Hello friends, good evening. So in the previous lecture, we discussed up to the part of greedy approach and what is the example and how the fractional knapsack problem can be solved, and I given one assignment to solve it. So in this class, we are going to be discuss about another greedy approach, that is Huffman coding. Okay. So before going to start this concept, I want to share certain presets with you which will be very beneficial for you whenever you are analyzing such kind of greedy algorithm. So suppose here I will show you a scenario, and based on that how we are going to be solve this Huffman coding. First of all, the scenario is transmitting data from one site to other site. Like you can take the example, suppose I'm sending a message. Okay. Sender is the transmitter and a receiver. The person who is receiving that is the receiver. So, and another one is encoding and decoding. Okay, so these are the scenario of Huffman coding. So, simple way is ASCII encoding, fixed length is 8 bits. So, if we are converting it to A equal to 0 into 61, B equal to 0 into 62. Okay, so this is the ASCII encoding. Okay, because here what we are doing, the length encoding we are doing for the 8 bits. Another one is sending strings of A, B, R, A, C, A, D, A, B, R, A. This is the string from TX to RX. So TX means transmitter X, RX is receiver X. So here the size of the data is 11 characters, 2 bytes per character, total is 22 bytes. So here, how you are going to be use this Huffman coding here, I will be explain in this class depthly. So first of all, similarly for other savings, the word processor file. So basically main concept of this Huffman coding is what? Here, basically we are focusing on reducing the memory. Okay. That is what? Compression. Okay. Compression means what? Like big size will be there. We just need to be reduce the size. Okay. That is what the idea is, to reduce the memory. Okay. Because suppose you are having a space. Okay. That space can carry, like suppose one bucket. That bucket can be filled with such water. Okay. Here size, memory size. But whenever we are talking about the computer codes, or whenever we are talking about the characters, how we are going to be compress it by the help of this particular Huffman coding. So this is the idea behind the Huffman coding. So now we'll move with the concept, like how technically this algorithm works. So basically, Huffman coding is otherwise known as lossy and lossless algorithm. Okay. So first of all, understand what is lossless. So lossless, every bit of data remains as is after it is uncompressed. That means whenever we are uncompressing, the data will be same. Okay. That means no loss will be erased. So all information can be restored. You can restore all the information again. So here lossy compression is reduces a file by permanently eliminating certain information, especially redundant information. So basically what this lossy compression is going to do, it is reduces a file by permanently eliminating certain information. So it will be reduced to certain file by permanently eliminating what now information, especially redundant information. That means whatever the information we are having, if that is a redundant information, then what will be happen? It will be automatically eliminated permanently from the system. Okay. So that is coming under lossy and lossless. So now I will be briefly explain what is the basic difference between the lossless and the lossy. Okay. So lossless is larger file sizes than lossy. So in comparison to lossy, whenever we worked with the lossless, it is larger file sizes than lossy. So it will have the larger file. But whenever we are going with the lossy, significantly reduced file sizes. That means it will be significantly, gradually, it will be reduced the file sizes. Coming to the written file quality with smaller size. So here whatever the written file is there, that quality is with a very smaller size. And loss is results in file quality loss. So it results in file quality loss. That is lossy. Even it is significantly reducing the file sizes, but it will be results in the file quality loss. So first of all, you understand Huffman coding, how lossless will work. So arithmetic coding, Ron length encoding. So Huffman coding works over the arithmetic coding and Ron length encoding. And coming to the lossy means it will be works again over the transform coding, discrete cosine transform, etc. So first of all, it will be works over the transform coding, discrete cosine transform, etc. So this is very important how the lossless is working. Lossless is uh, like how over the Huffman coding work over the arithmetic coding on length encoding and this transform coding, discrete cosine transform. These are all plays a very important role whenever we are working over this particular algorithm, that is Huffman coding. So the real-time examples you can take images like a GIF, a PNG or lossy will be goes with the JPG, audio, WAV format. But whenever we are going with the lossy, it will be goes with the MP3 and lossless, it will be works over the GIF. I hope you clear with the lossless and the lossy. What is the basic difference and how the Huffman coding work over the particular lossless algorithm. Okay. But whenever we are going with the other coding like transform coding, discrete quotient transform, that how work over the lossy algorithm. Okay, I hope you clear with this. So next we'll move with the Huffman coding and how the comprehension of the size of the particular bit is happening, that I will tell in this slide. So first of all, Huffman coding is known as lossless data comprehension algorithm. Why it is called the lossless data comprehension algorithm? Because here we are doing what? We are reducing the size, whatever the size is there, that we are reducing without affecting the size of the particular strings or characters. So for that reason, this algorithm is otherwise known as lossless data comprehension algorithm. Okay. And variable length codes instead of fixed size codes. So this algorithm has the variable length code instead of fixed size codes. And length of codes depend on the frequencies of corresponding codes. So whatever the length of the particular code is there, that always depends on the frequencies of corresponding codes. Based on the frequency of the corresponding codes, it will be work. Okay. So these codes called prefix codes, and this code also otherwise known as prefix code. Okay. So code assigned to one character is not the prefix of any other character. So it is not the prefix of the any other character. Hence, avoiding ambiguity. Why we are going with this? Because we just need to be avoid the ambiguity. Because what I mentioned, whenever you are going with a particular string or a character, the data loss will not be happen. But while you are working over this code assigned to one character, is not the prefix means what will be happen? So it can be raised with the ambiguity. Okay. For that reason only, due to that reason only we are working over the prefix codes. So okay, so now we'll see with one example. Now you see these are the character is given for the like alphabets, and here the code is given. So compressed output is 0011. So after compressing, the output will be comes with the 0011. We will see how it is working. Possible decompressed outputs are. So here if we are decompressing, it will becomes like AB, CCB, CCDD. Okay. So this is what this is. You can clearly mention here ambiguous. Okay. So now we'll move with the example to solve like how we can able to be solve this particular example. Okay. So now you see. So first of all, what we have to do? Now I said what? This is ambiguous. Why it is ambiguous? Because possible decompressed outputs. Because after decompressing, it will be comes like this: A, B, C, C, B, C, C, D, D. That is what it is ambiguous. Because while we are checking with the compressed output, it is coming with 0011. But whenever we are moving with this, you can see Huffman coding, example of unambiguous codes, prefix code. So this is unambiguous code, prefix code. If prefix code means you can see compressed output is 0011 already mentioned in this slide also. So possible decompressed output will be what? Unambiguous. Unambiguous means it will be moved with AAD. AAD, why AAD? That I will tell you because 0011. 0011 means it will be take with what? AA and D. So here the intent is to generate an algorithm. Okay, what is the main intention of this particular algorithm? It will be reduce size comprehension using variable length codes. So here the comprehension will be happen by using the variable length codes. Then unambiguous during decomprehension or decoding. So next one is unambiguous during decomprehension or decoding. So unambiguous will be happen during decomprehension or decoding. No loss of data. So here there will be no loss of the particular data whenever we are going with the this kind of Huffman coding. Okay. Next is Huffman coding, 2 steps. Step 1, build an Huffman tree from input characters. So first of all, what you have to do, if you understood these two things, then you can move with the like Huffman coding. Okay. So in this Huffman coding, what are the steps followed? So basically, whenever we try to solve the problems based on the Huffman coding, we just follow 2 steps. So first one is what? Build an Huffman tree from input characters. Based on the input characters, what we have to do, we have to build a Huffman tree. Then traverse the Huffman tree and assign codes to characters. Next, we have to do what? Once we build the Huffman tree based on the particular input, next we have to traverse the Huffman tree, assign codes to characters. Then once traverse, assign the codes to characters. So now you can see with the example here what? Here the Huffman coding. Step 1 is mentioned based on the input string is 15 character. So 15 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Total 15 characters is there. Okay. So why 8? 8 means 1. It is going with what? The 8 bits. 8 into 15. Okay. That is 120 bits. So here what we have to do, build an Huffman tree from input character. Same tree will be used at both TX and RX. TX means transmitter X, then RX means receiver X. So here what? Same tree, same tree has to be transmit over the TX and receiver also receive the same tree for encoding and decoding. So first of all, calculate frequency of each character in the TX string. So first of all, frequency calculation. So B1, okay, C is 6, C6 means 1, 2, 3, 4, 5, 6. How many C is present? That is your frequency. So A is 1, 2, 3, 4, 5. A is 5. D 1, 2, 3, 3. Okay, D is 3. So step 2, sort the character in increasing order of frequency. So now what we have to do? We have to sort the characters in increasing order of frequency. Increasing means it is going with now you see B1, D3. Okay, A5, C6. Increasing order of frequency, we sorted. Okay, so this is the step 2. So we'll see with the step. Next one is what? Next step 3 is create an empty node Z. Then we have to create an empty node Z. Assign the minimum frequency to the left child of the Z. So minimum frequency should be there at the left child of Z and assign the second minimum frequency to the right child of Z. So minimum frequency will be assigned to the left child and second minimum frequency is going to be assigned to the right child of Z. Set the value of Z as the sum of the above two minimum frequency. Okay. So based on that we have to do. So now you see BDAC. Previously also I can show you if you want. Okay. Here it will be clear for you. Now you see. Okay. Now you see. Step 2 BDAC was there. So here BDAC So 1, 3, 5, 6. 1, 3, 5, 6. Okay. So therefore, remove the two minimum frequencies from Q and add the sum into the list of frequencies. So first what? Remove the two minimum frequency from Q. Minimum frequency is what? 1 and 3. So that has to be sum up into the list of frequency. Denote the internal nodes in the figure above. Internal node 1 plus 3 is added 4. Then A and C. Step 5, add node Z to the tree. So now Z node, okay, 4 added to the tree. 1, 1 and this is for sorry, this is for B and D. So now you can see the tree is formed. Next slide. So next one you can see Huffman coding step 1. Repeat step 3 to 5 for all characters. So all characters here you see all the characters is there 1, 3, 5, 6. Okay. Here 4, 1, 3 BD. Next one is next again add 6, 3, 9. 9 means again it will be goes with 4, 5. Okay. So here step 3 is C 9. So 9 will be go there, then 4 and 5, then 1, 3. This is 5 is for A. Okay. So A, B, D, A. Clear? So next we have to go with the next step. Okay. Next step means repeat step 3 to 5. 3 to 5 again we have to repeat. 3 to 5 means what? 3 to 5. Okay. So 3 to 5 means you can see easily. This is here 13. 13 means what? 3 to 9. So 13. 13 means what? Here 9, 4. 13. 13, 6, 9. Okay. 6, 9. So here 6, 9 is 15. So now 13, 6, 9, 4, 5, 1, 3. Okay. So now B, D, A, C is certain. Next step is, so step 7 is for each non-leaf node assign 0 to the left edge and 1 to the right edge. Okay. 0 is 0 given, 1 to the right edge. Here also 0, 1. Here also 0, 1. Okay. Next step is step 2. Traverse the Huffman tree and assign codes to characters. So now traverse is A, B, C, D, 4 into 8, 32. Frequency is 5163, 15 bits. So 15, 5 plus 1, 6, 12, 3, 15. So the code will be 11, 100, 101. Size will be 5 into 2. Okay. So here 3, 1 into 3, 0, 6 into, 6 into 1. So next one is 3 into 3. That is total sizes if we are adding 9, 6, 15, 3, 18, 10, 28 bits. So with Huffman coding, tree along with compressed code, that is 32 plus 15 plus 28. All are we have to add it. Sum 75. So with ASCII encoding, how much will become? 15 into 8. 15 into 8, that is 120 bits. So now Huffman coding, for decoding, we traverse through tree to find the characters. So through tree, if we are traversing, then we can see 1, 0, 1. So that is D. Okay. So this is about your Huffman coding. You just go through this books. Any doubt, you can go through it and you can ask me in the next class. I will clarify you if there is any doubt from this particular example. Okay, just try to practice it. If there is any doubt, you just put in the comment box. I will try to resolve your doubts. Thank you.